everyone. So in continuation of our earlier lecture on statistical inferences, today we'll be learning few more topics. So in my earlier lecture we have learned what is type 1 error, what is type 2 error. Now we will see which is more important, why we should mainly we'll see we focus more on type 1 error. That's why we have that significance level, what I have mentioned. Significance levels is mainly with respect to the type 1 error. I did not mention about type 2 error. Why we focus more on type 1 error, why it is considered more important, we'll be discussing that. And then how to plot the OC curve, what is an OC curve, how to plot that, and then we'll discuss what is a power curve. Okay, so in hypothesis testing we focus more on type 1 error. Why? That you have noticed, we focus more on type 1 error. Why? Because see, when the first step is we specify H0, H1 and the significance level. What is the significance level? Significance level is the maximum acceptable probability of rejecting a true null hypothesis, isn't it? What is the significance level? Maximum acceptable probability of rejecting a true null hypothesis. So that is alpha. What? That is what? Type 1. I did not mention anything about type 2. That means what? Type 2 is not important. We will see that. So what is basically the null hypothesis? Null hypothesis is the hypothesis that requires no action to be taken, no money to be spent, or in general nothing to be changed. Already I have mentioned about when I talked about what is how to form the hypothesis. So that is my null hypothesis. Null hypothesis is the maintaining the status quo, like where we don't want to do any action. No, we don't have to do any, we don't have to spend any money, we don't have to change anything. So that is my null hypothesis. So say, like in my example, that machine that fills medicines in the 8 ml bottle. So there's a machine which fills exactly 8 ml medicine in this bottle. That is my null hypothesis. Remember, I have specified my null hypothesis mu is equals to 8. Then what I wanted to prove? I wanted to prove mu is not equals to 8. So see why we have focused here on type 1 error. Now suppose I have rejected a true null hypothesis. What happens if I have rejected a true null hypothesis? Suppose that the medicines that was actually producing 8 ml, actually filling up 8 ml medicines only in the bottle, but then the sample results what I got, we already saw when I discussed about the p-value. Remember, if you forgot, then please I suggest you to go back to those slides and see again. When I sometimes what happens, for a slight change, we can have different results, isn't it? So maybe for such samples we got such a result for which my value is falling in the rejection region. My value is falling in the rejection region means I am rejecting the null hypothesis. But what happens? But actually maybe my null hypothesis is actually true. That was a stray sample which I took and I got that value. So what happens? I have rejected the null hypothesis. When I have rejected the null hypothesis, that means the machine is not working properly. I'll have to change the whole machine. Maybe I'll have to invest crores of money for changing the machine, or whatever, spending lots of money, lots of time, energy, everything, which actually it is not necessary. Okay, so it is usually costlier to incorrectly reject the status quo than it is to do the reverse. So that's the main thing why we focus on type 1 error. So now knowing this, so hypothesis testing, our first step is we specify the hypothesis, null and alternate, and we specify the significance level. Significance level is totally depends on the null hypothesis, means significance level corresponds to the acceptable probability of the null rejection of the true null hypothesis. So now the question is, how do we understood why we had to focus on type 1 error. So now for a given applications, when we have to do hypothesis testing, so we'll have to frame our hypothesis in such a way so that our null hypothesis is that which maintains the status quo. So, and when it is that which maintains the status quo, and then the significance level should be such that we have to select the significance level such that so that we can even if there is some error, there will not be much harm. So there is, as I told you, depending on the situation, the significance level is selected. So when, as I also have mentioned, when I talk of p-value, the decision maker will decide based on different factors what should be the rejection region. So depending on the how costly it will be if I reject a true null hypothesis, how difficult it will be if I reject a true null hypothesis. Based on that level of difficulty, based on that level of expenses, I can decide my type 1 error probability. Okay, that is my value of alpha. Suppose it is a very critical application. So if I cannot manage to reject the null hypothesis for no reason, if I cannot manage to reject a true null hypothesis, very critical reason, because if I reject the true null unnecessarily, I'll spend crores of money. Then I will keep my type 1 error probability very, very less, maybe say 0.001. Okay. So however, maybe if my if some error I can manage, I don't need to bother much about the, even if there is a type 1 error, it will not make much of a difference, then I will keep my type 1 error probability a bit higher. Now thing is that why should I keep it higher? Because already in my first lecture on statistical inferences, I have already seen, which I'll again talk more details on it, which I have already seen, when I'm increasing alpha, my beta decreases. That means if I increase my type 1 error, my type 2 error decreases. If I decrease my type 1 error, if I take my type 1 error very, very less value, my type 2 error will become very, very high. Okay, one increases, the other decreases. So for situation where the type 1 error is very, very critical, I will have a very less type 1 error probability, but at the same time my type 2 error will increase. So since this, because of this relation, so wherever the situation that I can have I can bear a bit greater type 1 error probability, then I will take greater type 1 error probability, so that I get my type 2 error also reduces. Okay. So we will understand this with few examples. So first, consider this case. Assume that a 6-year-old children should average about 10 kg in weight, and that is considered normal. Assume that a 6-year-old children, on an average, their weight should be 10 kg. So what suppose consider that a sample of children from a low income neighborhood is to be tested for subnormal weight. Suppose in a slum area, like the children are malnourished. So government is trying to bring out some nutrition program. If the first they will first find out whether the children are really malnourished. If they are malnourished, some program will be, some nourishing program will start, government will start. If they find that the children are okay, the children weight of 6-year-old children, on an average their weight is 10 kg, then government need not start that program. So now see here, what will be my normal, what will be my null hypothesis, what will be my alternate hypothesis, what will be my significance level. So here my null hypothesis is definitely mu is 10 kg. Thus I want to maintain, definitely I will always want to maintain the status quo. That will I will, okay, so mu is 10 kg. But what I want to prove, that mu is less than 10 kg. Because if it is less than 10 kg, then I will have to start some nutritional program for the children of that slum area. So what I want to prove is less than 10 kg. Now here, if it is that, if I consider what to say, mu is equals to 10 kg, okay, and sorry, let's not take this way. For this example, what I want to prove is that mu greater than 10 kg. So what I want to prove, mu greater than 10 kg. Why I want to prove mu greater than 10 kg? If I want to prove mu greater than 10 kg, then I'll not have to start this nutritional program. Why? It actually totally depending on the situation that different hypotheses are formed. So here maybe if my intention is, if not required, I will not start the nutritional program. In that case, I will make the type alternate hypothesis is mu greater than 10. But see the significance here. So that means when my null hypothesis is 10, if I reject the null hypothesis, if it is true and I still reject the null hypothesis, let me first write it. Okay, so this is whether it's colon, mu is equals to 10. Okay. Then let us take, that will be more easier, where mu is less than 10. Okay, mu less than 10. This will fit more as an example. This we are taking just an example to bring to the point how we select the significance level. So here, if I take mu is equals to 10, so if my null hypothesis is rejected, then what happens? That this hypothesis will be accepted, H1 will be accepted, and the nutritional program will start. So if what happens, if by mistake the null hypothesis is actually true, see here, but null hypothesis is actually true, but I have rejected a true null hypothesis. Under what situation I have accepted it, rejected a true null hypothesis? That means if it falls in my rejection region. Null hypothesis is actually true, but the sample what I got, from the sample I found that no, null hypothesis, the value is fall in the critical region, so I will reject the null hypothesis. Then what happens? The nutritional program will start, an unnecessary expense to the government. Okay, but then you see the other way around. What happens? If the null hypothesis is not true actually, but I still accept it, that means a type 2 error. I got such a sample. From the sample I found that okay, null hypothesis is true only, but actually the null hypothesis is not true. Actually the sample what I got, that was some outlier I got, and I found that okay, the weight of the children is more equal or greater than 10, so that means I don't have to reject the null hypothesis. Then what happens? The nutritional program did not start. Now which will have more effect? See, if in the slum area, if the children, even if they don't need, if they get if the nutritional program is started, government will spend some money. That's all. But these children, definitely it will be good for the children only, because as it is, they are poor children, they will get to eat. So what? So here, if my type 1 error is not very serious, just that government has to spend some money. But if I commit type 2 error, what is type 2 error? Type 2 error means my null hypothesis is not true, but still I accept it. Then it may be dangerous. The children are malnourished, still the government did not start the program. So it will have a dangerous effect on the children. So here my type 2 error is very important. Understood the point? So in such case, hypothesis testing, we always specify the type 1 error, acceptable type 1 error. So this is the case where type 1 error is not very critical. So what I will do, I will specify a greater type 1 error, so that I get a lesser type 2. So maybe in standard type 1 error is usually 5% or 1%. Maybe I take a type 1 error of say 15%. Okay, fine. Poor children, even if their weight is fine, the comment if the null hypothesis, if by mistake also we have rejected the null hypothesis, okay, let the nutritional program start. So I am ready to accept it, 15% error probability. Understood? So now this is one example. So next is the next example. A drug company wants to test a new drug for the toxicity. It wants to test the new drug for toxicity. See here. So here what will be the null hypothesis will be, the drug is toxic. Alternate hypothesis, because what I want to prove, that it is not toxic. Okay, it is not toxic. Here again, as I told you, this formation of this hypothesis, it totally depends on who is trying to do. Here the drug company itself is trying to do. So drug company is what to say, its objective will be trying to prove that it is not toxic. But if some third party is trying to prove, third party will trying to prove that it is toxic. So then accordingly my hypothesis will be different. It totally depends on who forms the hypothesis and which is more important while forming that hypothesis. Alternate hypothesis is something which we always want to test, that is the alternate hypothesis. So my H1 is, it is not toxic. So now here the drug is toxic. Okay. So here, suppose here what happens, if I by mistake, if I reject the null hypothesis, by mistake if I reject the null hypothesis, then what happens? given the drug is toxic, I have rejected the null hypothesis, then what happens? Then it is proved that drug is not toxic. See the effect it will have. The drug is toxic, and you are specifying the drug is not toxic, so it will have a very, very dangerous effect. Okay, so in this case my type 1 error is very, very significant. In such case, maybe I will select my type 1 error will be say 0.0001. Let beta be more. We will see, even if the beta is more, it will not have much effect. We'll see what. But here, let beta be more, but we cannot manage a higher type 1 error, because a higher type 1 error means it will result a toxic drug termed as non-toxic. Okay. So now the question is, can we completely ignore type 2 error? Now in the second question, see, we have selected a very, very, very small type 1 error. That means our type 2 error will become very big. So that means, is it that we can completely ignore type 2 error? No, we cannot ignore, but there is a twist to it. We will see how. That's what. If the probability of making a type 2 error is very less, then the test may not be useful also. So we'll see how. Okay, because the trade-off between alpha and beta, we may find that we may need to increase alpha in order to have a reasonable values of beta. So that totally depends on the application, what alpha you will keep, which is more important, type 1 or type 2. Now calculating beta. Remember in the first lecture, I told two things that we'll be discussing. One is how to calculate beta. Though for a toy example, that is box of chocolate, I calculated beta, but that is a toy example that is not applicable for any, that is just to understand the concept. But calculating beta is not a very easy job. It is not straightforward. That's the reason I did not show how to calculate beta over there. Now you have enough in knowledge, so now we can see how to calculate beta. Secondly, I also mentioned one thing in that lecture itself. The null hypothesis always should be with equal sign. That why I will come here. Thirdly, why we focus more on type 1 error, that we have seen. Why we focus more on type 1 error, that we have seen here. Now how to calculate beta, and why null hypothesis we need a equal sign, that we will see here. So see, any sort of hypothesis testing, my backbone is my main CPU, I should say. My CPU is the sampling distribution. Everything I put data, I give to the CPU, and the CPU gives me the results, isn't it? So every data I give to the sampling distribution. From the sampling distribution, whatever result I get, based on the result only I give the decision. So for sampling, when I have the sampling distribution, what happens? My sampling distribution means it is one distribution which is normally distributed, and which has a mean, and its mean is what? Its mean is equals to the population mean, and it has a variance. Variance is population mean divided by population variance divided by sample size, that is the variance. Okay, forget about the variance. Now this sampling distribution, its mean is equals to the population mean. So if my hypothesis, if always I try to find out the data based on my null hypothesis, what we have hypothesized, that is mu is equals to 8. So when I find out the sampling distribution, in my sampling distribution, so my mean is 8. Okay, so if I don't have an equality sign, then I cannot have one sampling distribution. I'll have to have many distribution for each values of mu. If I write mu not equals to suppose that medicine example, that is mean is equals to 8. Mean not equals to 8 means non equals to 8 means I'll have to have distribution for all possible values of 8, isn't it? All possible say values of 8 means 7.9. For 7.9, that means I'll have to have a distribution whose mean is 7.9 and variance whatever it is. Then whatever, suppose 8.1, I'll have to have a value for distribution for 8.1. So that way I'll have to find out the alpha values for all the values of all different values of mu. That was the reason why, to simplify the process, my null hypothesis always need to have an equal sign, so that we can have one sampling distribution which mean is equals to the population mean. Now when we are trying to find out the type 2 error, for finding out the type 2 error means we have to find out the rejection regions, or basically type 2 error means we are not rejecting a true null hypothesis, means it is false but it is falling in the acceptance region. So definitely we need to have a sampling distribution. So when we have a sampling distribution, we need to have the mean of the distribution. So when the value is not equals to 8, what will be the value? So that means we will have different distribution for different values of mu. That's why calculating beta is not very straightforward. It's not always straightforward. That was the toy example, that box of chocolates, so we could do it very easily. So here, so hence there is a sampling distribution. Hence there is a sampling distribution of that for each unique value of mu. For each unique value of mu, there will be one sampling distribution, each producing a different value of beta. Okay, therefore beta must be evaluated for all values of mu contained in the alternate hypothesis, that is all values of mu not equals to 8. For all values of mu not equals to 8, we'll have to take mu not equals to 8, there can be any value, infinite values, right? So for all values of mu not equals to 8, we'll have to find out beta. So however, for practical purpose, we will see it is sufficient to calculate beta for a few representative values of mu. If we calculate if we take some few representative values of mu, then it is sufficient to find out the value of beta. Then this representative values of beta, for this values of mu, different values of mu, what beta we get, we can plot this, and what we got this plotting is nothing but it is called an operating characteristic curve. Okay, so we'll see what is an operating characteristic curve. So we have again taken the same example to plot the operating characteristic curve. So here you see what was our hypothesis. Hypothesis is mu is equals to 8, alternate hypothesis is mu not equals to 8. Significance level, we have considered 5% significance level only. So here when I have found out the significance level, see very carefully, z is equals significance level alpha is equals to 5%. When alpha is equals to 5% means what? If this is my distribution, that means this value, this area is 0.025 and this area is 0.025. Then I found out what is the z value corresponding to this. Z value corresponding to this is I think you remember it was 0.96 and minus 1.96. This is in terms of z, isn't it? But I need the value in terms of, to find out the rejection region, I may also need the value in terms of the actual parameter value, random variable. What was my random variable? My random variable was x. Based on that, I found out x bar, isn't it? So this z I got value converting from x to z. How we what is the z value? Z is equals to x bar minus mu by sigma, isn't it? This is how we calculate the z value. Now this, let me tell this as a this counterpart in the as a random variable. Say this is C1, this is C2. Then what is the z value? Minus 1.96 is equals to C1 minus mu is 8. And what was sigma? Sigma was in this example is I think 0.2 divided by 16. We have taken a sample of size 16 and standard deviation is 0.2. So similarly again 1.96 is equals to C2 minus mu 0.2 by root 16. So we calculate the C1, from here we calculate the value of C1, from here we calculate the value of C2. So C1 we get, if I can simplify it, C1 we will get I think 7.902 if I remember correctly, and C2 will be getting some 8.098. So my rejection region is mu is equals to 8. Mu is equals to 8. So my rejection region will start from 7.902 to 8.908. That means here I'm drawing the graph again. So if this is the thing, this is my rejection region, 7.902, and this is 8.098. Okay, fine. So this is my rejection region. Here this is 8. That means acceptance region means mu is equals to 8. Remember what is this acceptance region? I am repeating it again. Mu is equals to 8. So mu is equals to 8 means the, under what situation I will accept it? Okay, mu is fine 8, but still a bit of variance I can consider. That's what, that was my logic. Remember, bit of variance I can consider. So how much variance I can consider? Maximum, and this side it is 7.9 and this side it is 8.1. Maximum, this much variance I can consider. isn't it? That's what. So basically, that is, I have just told 7.9 or 8.1, but when I specify the significance level, from the significance level, I could find out what is my this critical region or the start of the rejection region. Okay, so now here, so I'll now we'll have to find out the value of beta for this different values of mu, because mu is not equals to 8. So different value, we have taken some representative value. So what we have taken? We have taken, see here, 7.80, and this side we have taken 8.20. We have taken equal, what to say, symmetric value both the side. So we have taken 7.90, we have taken 8.1, 7.95, 8.05. Okay. So now we have to calculate the type 2 probability. Type 2 probability means actually my null hypothesis is false, but I am accepting it. That means it is it should when the null hypothesis is false, but my value is falling in the acceptance region. That means my mu value is falling between 7.9 to 8.1, but actually it is false. So that is my type 2 error. So beta is probability that my x bar value falls within this range when mu is actually my mu is 7.95. Mu is not 8, but when my mu is 7.95, my x bar is falling within this range. That is my beta. So what is this corresponding to this x bar value? Corresponding to this x bar value, what is z value? I can find out. So this is the z value. So what is the probability of beta? It's 0.8300. From the z table, I can find out, and I can remember how do we find out this? I'm again repeating it. We got it from here, this portion, then this portion. So then this portion minus this portion will give me this portion. Okay. So this we found out for mu is equal to 7.95, my beta value is 0.8300. Similarly, I found out for mu is equal to 8.05, what is my beta value? I got the same thing, same beta value. It's symmetry. Okay. So considering this is a 7.902 and 8.098 is the rejection region. That's I have just now shown why this is the rejection region, corresponding to minus 1.96 and plus 1.96 for 5% significance level. We got this is the x bar value. Okay. So now we will consider for mu is equal to 7.10 and 8.110. We will see that if we calculate, we will get this value 0.4840. Similarly, if we calculate for 7.80 and 8.20, we will get this beta value. Okay. So for this representative values of mu, different values of mu, these are the values of beta we got. Okay. Now we can plot this value. Okay. So if we plot this value, this curve is called operating characteristic curve. Operating characteristic curve means where we are trying to plot beta for different mu. What is beta for different mu? Okay, where mu is not equals to 8. You see here the beauty of this curve. You see when my mu, actual mu, that means population mean, when my mean is very close to the hypothesized value. When my mean is very close to the hypothesized value, then what happens? Then my type 2 error is very high. Okay, when my mean is very close to the hypothesis value, my type 2 error is very high. It in fact, beta in fact approaches 1 minus alpha. Whatever alpha we have specified, beta approaches 1 minus alpha when my actual value goes very near to the hypothesized value. So see what happens when my my actual value is very near to the hypothesized value, then my type 2 error is very high. Meaning what? Means I am accepting a false null hypothesis. But you see, when my value is not very different, but very near to the hypothesis value, even if I am accepting a false null hypothesis, then also it will not have a very serious effect. That is one thing. Second point is that already I told you that when my null hypothesis is not rejected, that does not mean that I am accepting the alternate hypothesis. That does not mean that when the null hypothesis is not rejected, does not mean that I am accepting the null hypothesis. It may mean two things. It may mean I am accepting the null hypothesis. It may mean I am not able to reject the null hypothesis. So if I'm accepting the null hypothesis, that means I'm complacent. I'm okay, fine. My null hypothesis I have accepted. But I'm not being able to reject the null hypothesis means again I will do in future, again I will do the experiment, and again I will see whether really my machine is really working fine or not. I'll again check for the check whether my null hypothesis is accepted or rejected. I'll continue this experiment for 2 times, 3 times, 4 times, and if it is really, if my population value is actually really away from 8, a time will come when I'll see that actually it is falling in the critical region and the null hypothesis will be rejected. Okay, so that's what, when my even if I have a very high type 2 probability, since my value is very close to mu, it will not have a serious effect. That is the first point. Second point, on if the mu is really different, after 1-2 experiment, it will definitely come to the conclusion that null hypothesis is actually rejected. When I'll take one sample, again after some time I'll take another sample. For some sample may be biased, all sample will not be biased, right? So I may gradually see that my null hypothesis is rejected. That is the first point. Now, when my actual value comes very much away from the null hypothesis, when my actual value comes very much away from the null hypothesis, then type 2 error is very less. Means that times accepting a false null hypothesis is very less, and that is good, that is required, isn't it? That means when I require my type 2 error to be very less, I'm getting that. When it is very much away from the hypothesis value, my type 2 error is very less. Okay. So the OC curve shows that the probability of making the type 2 error is larger when the difference between the true value of the mean is close to the null hypothesis value, but decreases as the difference becomes greater. Okay. In other words, the higher probabilities of failing to reject the null hypothesis occur when the null hypothesis is almost true, in which case the type 2 error may not have serious consequences. Fine. Now there is one more concept, that is the last concept in this lecture which I will be discussing, that is power. Power is nothing but beta is type 2 error, power is nothing but 1 minus beta. So basically, as a practical matter, we are usually more interested in the probability of not making a type 2 error. And practically, if we see, we will be more interested in not making type 2 error. That is the probability of correctly rejecting a null hypothesis when it is false. Not making a type 2 error means when a null hypothesis is false, we are correctly rejecting it instead of accepting it. That is my power. The power of the test is the probability of correctly rejecting the null hypothesis when it is false. That is defined as the power of a test. So power of test is nothing but 1 minus beta. Beta is accepting a false hypothesis, so 1 minus beta is rejecting a false hypothesis. The graph of the power versus all the values of mu is called the power curve. This whatever OC curve we got, it's just the power curve is just the opposite of that. See, this is the power curve. OC curve is beta versus mu. And what is power curve? 1 minus beta versus mu. Okay. So my power is very less when my actual value is very closer to the null hypothesis value. When my actual value goes far away from the null hypothesis value, my power is very high. That is desirable. Okay. So the power of the test increases and approaches unity as the mean gets farther from the null hypothesis value. As the true value of the population parameter approaches that of null hypothesis, the power approaches alpha. When the true value of the population, it approaches near the null hypothesis value, my power becomes very less. It approaches alpha. That is, it approaches to the type 1 error, the value of type 1 error. Decreasing alpha decreases the power. Why? When it decreases alpha, beta increases. When beta increases, 1 minus beta decreases, isn't it? So decreasing alpha decreases the power. However, increasing the sample size increases the power. So fine, to conclude this, in this lecture today we have learned a couple of concepts. We have learned the relative importance of type 1 error, type 2 error, how we plot OC curve and what is its significance, the power of a test and how it varies with respect to alpha. Okay. In the next lecture, we'll cover a tutorial encompassing all the 3 lectures what we have done in statistical inference. There are more to statistical inference which we'll be discussing. First, before you forget all the rest, all the things what we have discussed, let's do a tutorial first, and then we'll be going to those lectures, other topics on statistical inference. So these are my references, and thank you guys.